Welcome to qnawire.
In this problem, for either state 1 or 2, neglecting the vertical component of acceleration, we must have that the sum of the forces in the y direction must equal to 0. And we'll take upward as positive here. So t times the cosine of theta minus w must equal to 0. So that means the tension in the chord T is equal to W cosine theta, where W is the weight of the ball. We also need to have that the sum of the x components of the forces must equal m, the mass of the ball, times the normal components of the acceleration of the ball. So from here we see that t sine theta is equal to W sine theta cos theta, and this is equal to mv squared over rho, the radius of curvature of the motion of the ball. But rho is equal to L sine theta. So this implies that the velocity of the ball, the end of the swing, v squared is equal to rho times W over m sine squared theta cos theta. And this is equal to L from above times G, which is W over m, and we remove one of the sine thetas by substituting in for rho. So that's times sine theta tan theta. So V1 is equal to the square root of L1 times G times sine theta 1 tan theta 1. And obviously for V2 it's the same, so that V2 is the square root of L2 times G times sine theta 1 tan theta 1. Tan sine theta 2 tan theta 2. So now that we have expressions for the velocity, we'll take the sum of the moments about y, and these moments must equal to 0. So the angular momentum about y is a constant. So what that tells us is that R1 m v1 must equal to R2 m v2. So angular momentum is conserved. Or substituting our expressions for v, we get that v1 times L1 sine theta 1 is equal to v2 L2 sine theta 2. Now we'll substitute our expressions for v into here. So we've eliminated r, and m cancels on either side, so we now substitute in for v. So this becomes L1 to the power 3 over 2 times G sine theta 1 times the square root of sine theta 1 tan theta 1 is equal to L2 to the power 3 over 2 times G sine theta 2 times the square root of sine theta 2 tan theta 2. So here we have an expression where if we square both sides, we see the g's obviously cancel. So if this expression becomes L1 cubed times sine of theta 1 cubed tan theta is equal to L2 cubed sine of theta 2 cubed, that's tan theta 1, and the right hand side tan theta 2. So here we have our relation among L1, L2, theta 1, and theta 2. So we have all of these in our expression. So that's our answer for part A. If the ball is now set in motion and we are given values for theta 1, L1, and L2 as follows, we need to calculate L theta 2. So theta 1 is given to be 35 degrees. L1 is equal to 0.8 meters, and L2 is equal to 0.6 meters. So using the equation above, we get that 0.8 cubed times the sine of 35 degrees cubed times tan of 35 degrees is equal to 0.6 cubed sine of theta 2 cubed times the tan of theta 2. We get that sine of the angle theta 2 cubed times tan of theta 2 minus 0.31320 is equal to 0. Hence, from here we can solve for theta 2, and we get that the angle theta 2 is equal to 43.6 degrees.